Good morning, all of you. Yesterday we discussed that electric potential due to the point charge. So next, in case of the electric potential, what is the units for that one? Potential V is equal to work done by that charge. That is nothing but the joule per coulomb, or this is also called, we are calling that one is the volt. How we define this volt? How we define this volt? Observe, V is equal to W by Q. That is, 1 volt is equal to 1 joule per 1 coulomb. Electric potential at a point is said to be 1 volt. One more time. Electric potential at a point is said to be 1 volt. Means if 1 joule of work to be done, if 1 joule of work to be done to bring a unit positive test charge, one more time, to bring a unit positive test charge from infinity distance to the particular point in the electric field, that one is also against the electric field. Against the electric field. So, how we define this electric potential? Electric potential at a point is said to be 1 volt, not potential, volt definition. Electric potential at a point is said to be 1 volt, means 1 joule of work to be done to bring a unit positive test charge from infinity distance to a point against the electric field. That is, we are calling the 1 volt. In case, if 2 volts means, what is the meaning of 2 volts? That is nothing but the 2 volts is equal to, this is the 2 joules per 1 coulomb. So here work done is equal to 2 joules. Here work done is equal to 1 joule. Why? Because this is the 2 volts. 3 volts means to bring that charge from infinity distance to the required point. So here work done is equal to how much? 2 joules or 2 joules. 3 volts, same, 3 joules per 1 coulomb. Okay, right. So next one is the, already we derived the expression, that is the electric potential due to the point charge. That is, V is equal to 1 by 4 pi epsilon naught into Q by R. Q by R. So right now we draw the graph in between the potential and the distance. Graph, that is the VR graph, potential and distance, not the velocity and distance, potential and distance. If you draw the graph, so take, this is the x-axis and this one is the y-axis. Take R value is on the x-axis, potential is taken on the y-axis. If you draw the graph, observe here, this one, from this, V is inversely proportional to R. If R value is increases, compulsory potential value is decreases. R value is increases, potential is decreases. Why? Because both are, how those two are related? Inversely proportional. One value is increases means compulsory, another value is decreases. Inversely proportional, not directly, inversely proportional. So here we are getting the graph like this. We are getting the graph like this. Here this means V is inversely proportional to R. So here if you draw the graph in case of the electric field intensity, this one is the E is inversely proportional to R square. E is inversely proportional to R. Observe the difference. Okay. So here no need this one, no need this first graph, right? Means I am rub that one. Yes. So this is only graph. V is inversely proportional to R. When R value is increases, observe, V value is decreases. R value is increases, V value is decreases. Okay? Right. So next one here, next continued topic. So electric potential at a point. Electric potential at a point due to system of charges. System of charges. Electric potential at a point due to system of charges. Due to system of. So in the previous one, we have find out the electric potential due to the single charge. That is that V is equal to 1 by 4 pi epsilon naught into Q by R. In case if they are given, this is the first charge something Q1, this is the charge Q2, and this is the charge Q3, and this is the charge Q4. So many charges are there, not 4, so many charges are there. We want to find out the electric potential at point O. We want to find out the electric potential at point O. Here separation between the point O and charge Q1 is R1. Point O and charge Q2 is the R2. And point O and the charge Q3, this is the R3. And this one is the R4. So due to the first charge, electric potential is the V1. V1 is equal to 1 by 4 pi epsilon naught into Q1 by R1. What about the V2? That is equal to 1 by 4 pi epsilon naught into Q2 by R2. V3 is equal to something, same one. So here net potential at point O, or maybe total potential due to the system of charges at point O is V. V is equal to, that is nothing but the V1 plus V2 plus V3 plus V4. So here we are taking only 4 charges. So that's why we are writing up to the V4 only. In case if we are taking the n charges, then that one is equal to V1 plus V2 plus V3 plus and so on plus Vn. Here we are taking only 4 charges. That's why V is equal to, here 1 by 4 pi epsilon naught is the common in all the terms. 1 by 4 pi epsilon naught into, so V1, that is nothing but the Q1 by R1 plus Q2 by R2 plus Q3 by R3 plus Q4 by R4. In case if you are taking the n charges plus and so on, Qn by Rn. Okay, so this is the electric potential at a point due to the system of charges. In case of the electric field, this is the scalar physical quantity. That's why we are just ordinary. We are using the ordinary algebra. Means 1 plus 2 plus 3 plus 4, that is equal to how much? Not the vector algebra. In case of the electric field intensity, in that situation we are using the vector algebra, that is the E bar net is equal to E1 bar plus E2 bar plus E3 bar plus and so on En bar. That is the vector algebra. 1 plus 2 is equal to how much? 1 plus 2 is equal to 3. This is right in case of the scalar physical quantities, not in case of the vector physical quantities. This is 1 plus 2 is equal to 3. That is right in case of the scalar physical quantities. But in case of the vector physical quantities, that is not the correct one. So observe, this is the one unit, something 1 Newton, and second one, this is the 2 Newtons. Here Newton, that means there is nothing but the force. Force is the vector physical quantity. What is the net force acting on this particular point? So here angle they given, that is equal to something 30 degrees. In this situation 1 plus 2, no, that is the wrong one. So vectors, in case of the vectors, that is the wrong one. So here we are using the parallelogram law of the vectors, first year concept. Resultant R is equal to square root of a square plus b square plus 2ab cos theta. Here electric field intensity is the vector physical quantity. So we are using this formula at that situation. But in case of the electric potential, this is a scalar physical quantity. So we are adding just using the ordinary algebraic rules. 1 plus 2 plus 3 plus 4 is equal to how much? Just ordinary algebra. This is a vector algebra. Okay. So that is the difference. Try to observe it. Next, electric potential due to the dipole. Electric potential due to the dipole. Electric potential due to the dipole. Dipole means electric dipole. Here we are discussing about the electric dipole. Magnet is also dipole. That is the magnetic dipole. Here electric dipole. What is the electric potential due to the dipole or maybe electric dipole? So actually in first lesson we learned that is the in electric charges and fields we are already learned that. So two equal and opposite charges. Two equal and opposite charges. One is the plus q charge and second one is the minus q charge. Two equal and opposite charges are separated by certain distance, something to a distance. That arrangement we are calling the electric dipole. Two equal and opposite charges are separated by certain distance. That arrangement we are calling the electric dipole. Okay, so here electric dipole moment. Electric dipole moment is denoted with the letter P. So this is the vector physical quantity, therefore P bar. Electric dipole moment, that is defined as the product of the magnitude of either charge, this one or maybe this one, magnitude, into distance in between the two charges. That is P bar is equal to 2aq. So P bar, this is the electric dipole moment. Electric dipole moment is equal to 2aq. So in some books they are given 2lq also, right? No problem. That is the separation between the two charges. That is the separation between the two charges. So here we are calling this is the vector physical quantity. What about the direction? Its direction is from minus q charge to the plus q charge, means from the negative charge to the positive charge. That means in this direction. This is the direction of P bar. Direction of P bar. So right now we want to find out the electric potential due to the electric dipole. At which point? On the axial point or on the equatorial point? We are find out one by one. So observe that one. Here I am taking this is the electric dipole. This is the negative charge and this one is the positive charge. These two charges are separated by a distance of 2a, or maybe I am reducing that length. Okay. So this is the positive charge plus q charge. So this one is O is the midpoint. O is the midpoint. Right now we want to find out the electric potential at a point on the line that is passing through the midpoint of the dipole and make certain angle theta with the horizontal. Here this one is the angle. This is the angle. Okay. Or maybe you just adjusted this one. This is the positive charge. Okay. Right, this is the negative charge and this one is the positive charge. Observe. So here dipole moment is in this direction. This line makes an angle theta with the electric dipole moment. So many books they are given differently, no problem. This is also right. So here this angle is equal to theta, means this line which one we are taking, that one makes certain angle theta with the axial line. What is axial line? The line which is passes through the both the charges of the electric dipole, or maybe. So this line makes certain angle theta with the electric dipole moment. Already we know that this direction of the electric dipole moment from negative charge to the positive charge, means in this direction. So here this line makes an angle theta with the electric dipole moment. electric dipole moment. So we want to find out the electric potential at point Z. At this point, we want to find out the electric potential. So the point is at a distance of r meters from the midpoint of the dipole. This is the r meters distance. That is the r meters distance. So observe, we want to find out the electric potential at this point means, first of all, find out the electric potential due to the positive charge and find out the electric potential due to the negative charge at point Z. So observe, this one is equal to some distance. How much this one we don't know. Yes, I am giving you name. This is the A and this one is the B. That is the B. Right now here this distance is equal to BZ. That is the BZ distance and this is the AZ distance. So first of all, you write the electric potential due to the positive and negative charges. So due to the positive charge I am taking electric potential is equal to V1 and due to the negative charge I am taking electric potential is equal to V2. So we are writing here electric potential due to the positive charge. Due to the positive charge V1 is equal to 1 by 4 pi epsilon naught into, due to the positive charge 1 by 4 pi epsilon naught into Q by R. Here charge is equal to Q, distance is equal to AZ. That is the Q by AZ. Q by AZ. Next one, electric potential due to the negative charge. We are taking that is the V2. V2 is equal to 1 by 4 pi epsilon naught into minus Q by BZ. Minus Q by BZ. So therefore net potential at point Z is equal to net potential at point Z. So net potential at point Z we are taking Vz, that is equal to V1 plus V2. That is equal to V1 plus V2. Just ordinary algebra only. We are using here, we are using the just ordinary algebraic rules. Why? Because that is a scalar physical quantity. Therefore, V is equal to 1 by 4 pi epsilon naught into, that is a common in both the terms. Okay. Q is also common into. So here 1 by, this one is nothing but the 1 by AZ minus 1 by, why? Because you write total one, first you write the total one. 1 by 4 pi epsilon naught into Q by AZ plus 1 by 4 pi epsilon naught into minus Q by BZ. Minus Q by BZ. So here from this one V is equal to Q by 4 pi epsilon naught into 1 by AZ minus 1 by BZ. Right now we have find out the AZ and BZ values and those values we are substituted here, then we are getting the electric potential at point Z. Okay, for that purpose draw the, first you draw the perpendicular from the point A to the on the line OZ. Perpendicular, this one is the perpendicular. Yes. Here is also, sorry for this one. Yes. V1 is equal to, this is the electric potential due to the positive charge 1 by 4 pi epsilon naught into Q by AZ, and due to the negative charge V2 is equal to 1 by 4 pi epsilon naught into minus Q by BZ. Right. So here we are using this space also. Right. Observe. So extend this OZ and draw the perpendicular from point B onto the OZ line. This one is the perpendicular. So here is also angle is equal to 90 degrees. Perpendicular. So from these two triangles, something this is the M and this one is the N. from these from this triangle AZN, from this triangle AZ must and should equal to the NZ. Why? Because observe here, if you are taking this one is the triangle like this, compared to these distances, if this is the very small, when compared to these two distances, this is the very small, means in that situation these two are equal. These two are equal according to the geometry only. So means here AZ is equal to AZ must and should equal to the NZ. At the same time, one more thing here. So MZ is equal to the BZ. So actually here this separation is the very less. Actually here total separation is equal to 2A. So compared to this distance, here R value is the very more. R value is very more comparative to the A. Here R value is very more comparative to the A. In that situation, AZ must and should equal to the NZ and BZ must and should equal to the MZ. That is the BZ is equal to the MZ. BZ is equal to the MZ. When this distance is very small, this separation is very small, in that situation only that one is possible, otherwise that is not possible. Okay, so we will find out, first we will find out NZ and MZ values. So observe this triangle, here triangle, this one is the ONA. So we want to find out the ON is equal to how much? ON is equal to how much? First observe this triangle. This is the N and this is the A and O. We want to find out the AN is equal to how much? ON is equal to how much? OA they given, that one is equal to A. That one is equal to A. Here angle is equal to theta. That is equal to theta. So we want to find out the ON value. To find out the ON, take cos value. Cos theta is equal to adjacent side by hypotenuse. So that is nothing but the ON by, that is the OA. Therefore ON is equal to OA into cos theta. OA is equal to small a into cos theta. This is the value of the ON. So here ON is equal to A into cos theta. Similarly, OM is also equal to A cos theta. Same, take the triangle, you find out the OM and ON values. So here this is in exam point of view, no need to reprint this one, you directly write it. So right now observe, ONZ is equal to how much? NZ is equal to how much? That is nothing but the NZ is equal to OZ minus ON, or maybe if you observe this one, ON plus NZ is equal to OZ. ON plus NZ is equal to OZ. We want to find out the NZ is equal to how much? NZ is equal to, this is the OZ minus ON. OZ minus ON. NZ is equal to OZ. OZ means that is nothing but the R minus ON means A cos theta. That is the A cos theta. Similarly, BZ is equal to how much? BZ at the same time MZ. So here MZ is equal to R plus A cos theta. Why? Because this is up to here. OZ is the R and this one is equal to A into cos theta. For this value, we are added the OM value. Therefore, R is equal to, R plus A cos theta is equal to MZ. R plus A cos theta is equal to MZ. Substitute these values in this equation. So here these are the equal means, therefore potential V is equal to Q by 4 pi epsilon naught into 1 by, so Az is equal to Nz minus Bz is equal to Mz, that is the 1 by Mz. So substitute Nz value and Mz value in this equation. Therefore, V is equal to Q by 4 pi epsilon naught into Q by 4 pi epsilon naught into this one is equal to 1 by Nz is equal to R minus A cos theta minus Mz is equal to 1 by Mz is equal to R plus A cos theta. R plus A cos theta. So simplifying that one, therefore V is equal to Q by 4 pi epsilon naught 4 pi epsilon naught whole into, that one is equal to LCM. How much is the LCM here? A plus R cos theta into A minus R cos, R plus A cos theta into R minus A cos theta. R plus A cos theta into R minus A cos theta. That is the LCM. Therefore, here we are getting the R plus A cos theta minus of, this is the R minus A cos theta. So therefore V is equal to Q by 4 pi epsilon naught into, separate those terms, R plus A cos theta minus R minus of minus plus A cos theta whole by, this is the R squared minus A squared cos squared theta. R squared minus A squared cos squared theta. Here R cancel. At the same time, one more thing, R is very more than that of the small a. Therefore, A square cos square is negligible. A square cos square theta, that is the negligible value. Comparative to the R value, A is the very minute one. So that is, we are neglecting that term, that is the A square cos square theta. Therefore, V is equal to Q by 4 pi epsilon naught into, this one is equal to A cos theta plus A cos theta, that is the 2A cos theta by, this one is equal to R square. So therefore V is equal to 1 by 4 pi epsilon naught into, V is equal to 1 by 4 pi epsilon naught into 2AQ. We are writing that when 2AQ is nothing but the P bar, that is the electric dipole moment. 2AQ is nothing but the P into cos theta by, this one is the R square. This is the electric potential at this point, means at point Z, due to the electric dipole. Here we are writing this one in the vector form also. So we are saying the electric potential is the scalar physical quantity. How we write that one is in the vector form? Yes, we will write it. Why? Because dot product of the two vectors is a scalar physical quantity. Dot product of the two vectors is a scalar physical quantity. Therefore, here we are writing that one is 1 by 4 pi epsilon naught into P bar dot R bar by R cube. This is the scalar form. We are representing that electric potential in terms of the vector notation, but this is the scalar. Electric potential is the scalar. Dot product of the two vectors is a scalar physical quantity. Here we are getting P R cos theta by R cube. R cancel, therefore P cos theta by R square. Same value. That is not changes. That one does not changes. So this is the electric potential due to the electric dipole at a point on its axis. So next one, right. So here we are getting the electric potential V is equal to 1 by 4 pi epsilon naught into P cos theta by R squared. P cos theta by R squared. In case, what is the electric potential due to the dipole at a point on the axial line? First of all, what is axial line? Try to observe first. So, what is the electric potential due to the electric dipole at a point on the axial line? Axial line means the line which is passes through the both the charges of the electric dipole. Means this is the axial line. This is the axial line. Axial line. The line which is passes through the midpoint of the dipole and perpendicular to the axial line. We are calling this is the equatorial line. Equatorial line. This is the axial line and this one is the equatorial line. How we define the equatorial line? The line which is passes through the midpoint of the dipole and perpendicular to the axial line is called as the equatorial line. We have find out the electric potential due to this electric dipole at a point on the axial line, at a point on the equatorial line. Observe that one. Axial line means right now that one makes an angle theta is equal to 0. In the previous one we are taking this one is equal to theta. Here we are find out the electric potential. But right now that line is this is the axial line, means that one makes an angle theta is equal to 0. When theta is equal to 0, that is nothing but the axial line. Axial line. In this situation, electric potential at a point on the axial line is equal to 1 by 4 pi epsilon naught into P into cos 0 by R square. Cos 0 is equal to 1, therefore 1 by 4 pi epsilon naught into P by R square. P by R square. This is on axial line. This is electric potential due to the electric dipole at a point on the axial. Right now the Z is on this line, on that line. Okay. Next, if theta is equal to 90 degrees, that is nothing but the equatorial line. That is nothing but the equatorial line. So when theta is equal to 90, that one is nothing but the equatorial line. At that situation, observe V equatorial is equal to 1 by 4 pi epsilon naught into P into cos 90 by 90 degrees by R square. Cos 90 degrees is equal to 0. That is equal to 0. Therefore, V equatorial is equal to, that is the 0. So on this line, if you take any point, that the electric potential must and should become 0. Here we are calling this plane is we are calling the null plane, means potential is equal to 0. This is also called as the null potential points. At any point on the equatorial line, net potential must and should become 0. Must and should become 0. This is the electric potential due to the electric dipole and on the axial line and on the equatorial line. Okay, once you practice this one, that is very helpful to you in the board purpose. We are using these formulas in the objective purpose also. We are discussing that one in the next video. Okay, all of you, bye.